So when you're naming ionic compounds, a lot of times you're going to be dealing with metals that have multiple oxidation states, aka, I mean, if we take a look at, let's say, cobalt right over here, cobalt can either lose 2 electrons or 3 electrons. All right. So let's say if I have cobalt, let's say if I have cobalt and I lose, let's say, 3 electrons. So if I lost 3 electrons, then that means I'm going to have a +3 charge. And let's say if that's bonded to oxygen. Now remember that oxygen is in group 6A, right? If we name the groups 1, this is group 1, this is group 2, right? Basically just columns in the periodic table. We skip the transition metals because the transition metals are funky. We have group 3A, group 4A, group 5A. This right over here is group 6A. What this 6 represents is basically that oxygen has 6 valence electrons, meaning that oxygen has 6 electrons in the outermost shell. All right. Now, oxygen and all atoms, right? All atoms, they want to get to 8 valence electrons. Some atoms will lose electrons in order to get to 8 valence electrons, and some atoms will gain electrons. Now, in this case, if you have 6 valence electrons and you want to get to 8 valence electrons, it's much easier to gain 2 electrons than to lose all 6 of the valence electrons. So you're left with the electrons in the other shell, right? It's much easier to just gain 2 electrons. So in this case, oxygen is going to gain 2 electrons, and if you're gaining 2 negative charges, well, it's going to be a -2, right? You're going to have a 2 minus charge, right? If you gain 2 electrons, you're going to have extra 2 negative charge. So using the ionic compound naming, you're going to get CO2, and then this is going to be O3. If you were to name this compound right over here, now we know how to like sort of kind of create the compound, but if you were to name it, you actually have to be specific, all right? So in this case, this is going to be copper. Sorry, it's not copper. Cobalt. You're going to put a 3. Cobalt 3 oxide. This is how you're going to name it. All right. So you would name this right over here kind of the same as you would name a normal ionic compound, right? Remember the metal? The name of that doesn't change, as well as the non-metal right over here, the oxygen. Remember that you have to end it with an IDE. So oxygen becomes oxide, right? You always have to end with that IDE if you're dealing with just kind of the regular element, right? If you're dealing with polyatomic, don't do anything. But if you're dealing with a regular element, put an IDE at the end. The only thing you have to do differently is you have to put this 3 in Roman numerals. So you have to know your Roman numerals. But essentially, this Roman numeral represents the number 3 because, well, you have 3 here, right? Cobalt 3 plus. It wants to lose 3 electrons, right? Let's say if we were to have cobalt, let's say if we were to have cobalt 2 oxide, well, this would look a little bit different, right? Cobalt 2 oxide, what this is implying is that we have a so if we have a cobalt and there's a 2 right over here, that kind of implies that we're dealing with a cobalt that wants to lose 2 valence electrons, right? It wants to form an ion with a 2 plus charge. While oxygen, it wants to gain 2 electrons from the cobalt, right? Do crisscross, you're going to get CO2, O2. Now we can simplify this, right? Because remember, ionic compounds need to be in the simplest form. So in this case, if I divide everything by 2, imagine if we divided that by 2. I know it seems a little bit cursed, but we would get just CO and then O. All right. Notice how there's like these invisible ones, right? If I don't put any coefficient on any subscript, that just implies that I have a coefficient of 1. All right. So there's 1 cobalt and there's 1 oxygen. All right. So yeah, this is cobalt 2 oxide and this is cobalt 3 oxide. All right. Cobalt 3, you have a 3 plus charge right over here, right? Starting out with this 3 plus charge because it wants to lose 3 electrons, but cobalt 2 oxide, it wants to lose 2 electrons. All right, now let's say if we have this compound right over here. Fe is iron, and Cl is chlorine, all right? Now, how do we name this? Well, you might remember that in order to name an ionic compound, right, what you're going to do is you're going to take the metal, you're going to keep that the same, and then remember chlorine turns into chloride. Now, the problem with this name, though, is that iron has multiple oxidation states, right? Iron can be +2, iron can be +3, right? So there's a little bit of a problem here. So how do we determine if iron in this case is a +2 compound or if it's a +3 compound? What can we do? Well, we can imagine iron, let's just say it has a plus, let's say it has a, I don't know, an X plus charge. All right. Either way, whether iron is a +2 charge or a +3 charge, notice how iron is always having a positive charge because it wants to give away electrons, right? Now we know that chlorine has a -1 charge. It's a nonmetal, right? It wants to gain electrons. So chlorine has a 1- charge. So if you were to do crisscross right over here, you're going to get Fe1 and Clx. All right. We don't know what X is, but maybe we can find X. Now notice how in our original formula right over here, we have Fe1 and Cl2. So X has to be equal to 2, right? Because if I do crisscross like this, I get Fe1, which matches up with what I have originally, and then Clx. Well, if I see a 2 here, well, then I know that X has to be 2 because it's in the same location, right? So that means that Fe has to have a 2+ charge. So if I want to name it, I just put a 2 for my Roman numerals. And yeah, iron 2 chloride. That's going to be the answer. Worst comes to worst, just guess and check. But yeah. Also, you have something known as hydrates. Hydrates, you can think about what you use to hydrate yourself, water. Hydrate is literally just water molecules, all right? So sometimes for an ionic compound, you have sort of water molecules that attach to the ionic compound. And that's hydrate, that's a hydrate. Now, in this example, the way you would name it is, this right over here is calcium chloride. Calcium chloride, right? Remember, chlorine turns into chloride, right? The first thing stays the same, and in your nonmetal, chlorine ends with an IDE, so it turns into chloride. Now, what you're going to do is you're always going to put a hydrate at the end. So you're always going to put a hydrate at the end. And it's like the covalent compound thing, right? You look at the basically sort of the coefficient and you see that there's 2 water molecules. So it's going to be dihydrate. So the name of this would be calcium chloride dihydrate. And that's going to be the answer. All right. So you literally just name it normally and you just add a hydrate with its with basically the amount of it, right? And that's pretty much it. Let's say if we have this, all right. Sodium is Na. Carbonate is this CO3 that you see here. So carbonate is CO carbonate. Remember for polyatomic ions, you actually don't, it does not end in IDE. So you don't do sodium carbonide or something like that. All right, for polyatomic, it stays the same, the name. Now you're going to do hydrate. You're going to add a hydrate at the end. And how many hydrates do you have? How many water molecules do you have? 10. We have 10 water molecules. So we're going to put a deca here. So we're going to have sodium carbonate decahydrate. That's going to be our answer. All right, so I want you to notice something about covalent compounds. I should have talked about it last video. But notice how the least an electronegative, so least electronegative, and least electronegative, that's going to be to the left. So if you take a look at some examples, right? Notice how in carbon monoxide, carbon is right over here. Oxygen is right over here. Remember that from electronegativity, oxygen is going to be more electronegative than carbon. I will make another periodic trends videos because my old periodic trends video is so bad because like I did not know how to edit. So it was basically like a podcast of me explaining everything. But basically, oxygen is going to be more electronegative than carbon. So the least electronegative atom is to the left, and the more electronegative atom is going to be to the right, right? This is why CO, it's pronounced carbon monoxide, right? This is why the formula for carbon monoxide is CO, not OC, right? You might be wondering, right? Why do we put the carbon first? Why don't we just put the oxygen first? Well, that's the reason why. If you took a look at nitric oxide or nitrogen monoxide, well, take a look here. Nitrogen is less electronegative than oxygen, so it's going to be to the left, right? And yeah, that's pretty much it.